Relativity. Relativity is a concept that was devised by Einstein. The German physicist thought up the entirety of it in his free time while working in a Swiss patent office. That's right, he thought up a theory which still holds its own after 100 years in his head during his free time. The theory of relativity is split into two main theories. The special theory of relativity, published in 1905, which is the one we'll be covering today, and the general theory of relativity, published in 1915, which we'll cover in the next video. The special theory of relativity applies to uniformly moving objects. A uniformly moving object is an object possessing a constant speed without any acceleration or deceleration. For example, the Earth moves at 30 kilometers per second. It won't go up to 40 kilometers per second or come down to 20 kilometers per second. So, special theory of relativity will apply. Whereas a car is continuously accelerating and decelerating. So, special theory of relativity won't apply. One of the most popular statements relativity makes is that the state of rest and the state of motion are relative. This may seem a bit illogical at first, but that's just because we're all used to taking the Earth as our common perspective. We go to a void with nothingness everywhere, and the same scenario plays out. As our common perspective is gone, we realize that person B is equally as right to say that he's at rest and everything else is at motion. And relativity is, in fact, logical. There isn't any difference between the two. It's just that the first one messes with our natural instinct that the Earth is the only correct perspective. Another prediction is that of simultaneity. Einstein predicted that simultaneity is also relative. For example, let's return to our previous situation, except this time a bolt of lightning strikes on two separate sides. Bolt A ahead of person B and bolt B behind it. For this experiment, we will assume both people have instantaneous reaction times. Relative to person A, both bolts land simultaneously, but person B will see that bolt A lands before bolt B. Why is that? Well, light has a finite speed, so as person B is moving away from the light of bolt B and towards the light from bolt A, the light from bolt A reaches his eye slightly faster. Very slightly, about 0.000011% faster. That's a very small difference, but a difference nonetheless. In this situation, the difference is too small to be noticeable by a human being. But if you compare it to rain, if your car moves towards the rain, it seems to be going just slightly faster than when you're driving your car away from the rain. The same phenomena is applicable for light, except that light is much, much, much faster. There's a problem that is raised with all of this considered. Let's go back to that scenario, but this time person B turns on a flashlight. For person B, the speed of light will be c, but for person A, the speed of light will be c plus the speed of the car, since speeds are additive. But this is in clear violation of one of our previous statements that the speed of light has to be c from all perspectives. So how does relativity deal with this problem? The answer is time dilation. In classical physics, time is a constant, an absolute construct which cannot be changed or tinkered with. However, in relativity, this isn't the case. There are two ways time dilation could occur: gravity and motion. I'll be covering gravity next video where we talk about general relativity, since general relativity is all about gravity. But motion gives us the answer to our speed of light problem. Due to the phenomena of time dilation, person B will notice that person A is moving slightly faster than usual, and person A will notice that person B is moving slightly slower than usual. This won't be a very noticeable change since the car is so slow. Assuming the car is moving at 60 kilometers per hour, the difference in the speed of light will only have to be about 0.0000055%. So time will only slow down by 0.0000005%. And then the paradox will be avoided, and that is time dilation in a nutshell. Time dilation has been proven with atomic clocks. But as I said before, you probably won't see the difference as 60 kilometers per hour is minuscule compared to the speed of light. So time dilation would be only about 0.0002 seconds every hour. Just to put that into perspective, that way it would take over 6 months to experience just a second of time dilation. This is going to conclude this video. I hope you enjoyed and learned something today. Like and subscribe. And if I made any mistakes in this video, then leave it in the comments below. And I'll see you guys in the next video. Bye.